Today, large language models are everywhere. They craft emails, compose music, even revolutionize scientific research. They speak, they create, they innovate, seemingly with limitless capacity. But this incredible power, this seamless intelligence, comes with an unseen, staggering price tag. Beneath the sleek interfaces and instant answers, a colossal machine churns, consuming unimaginable amounts of computational power and energy. It's a hidden footprint that quietly threatens to limit AI's future, pushing its most advanced forms out of reach for many. To understand this challenge, we must first grasp how these models actually think. At their heart, LLMs are vast digital brains, composed of billions of interconnected parameters. They're trained on truly massive amounts of text and code, learning to predict the next word in a sequence with astonishing accuracy. The secret sauce, the core mechanism allowing them to truly understand context, how words relate to each other across long sentences or even entire documents, is something called the attention mechanism. It's what allows an LLM to distinguish between bank as a financial institution and bank as the side of a river based on the surrounding words. It grants them their remarkable ability to comprehend and generate coherent, contextually relevant text. Now, here's where the hidden problem emerges. The original attention mechanism, the one that powered the groundbreaking transformer architecture, operates under a principle known as full attention. Imagine a grand orchestra. Every single musician on stage, from the first violin to the last percussionist, is trying to listen to and react to every other single musician at all times. It's a marvel of coordination, but as that orchestra grows larger, as more words enter the LLM's thinking space, the number of connections each musician needs to manage skyrockets. This isn't just an additive growth, it's quadratic. Doubling the size of our orchestra doesn't just double the connections, it quadruples them. This quadratic complexity means the computational cost and memory required by LLMs explode with every increase in their context window, in the amount of text they can process at once. This isn't just an inconvenience, it's a fundamental bottleneck, limiting how powerful and how long-winded our AI can truly be before becoming impossibly expensive. For years, the mantra in AI was simple: bigger is better. More parameters, more data, more processing power, and performance would inevitably improve. And to a certain extent, this holds true. But what if the real genius wasn't just in adding more and more raw power, but in thinking differently about how that power is used? What if the next leap forward for AI isn't about building a larger, more sprawling orchestra, but about teaching it to play just as beautifully, with fewer, smarter connections? The misconception is that we simply need larger chips and more electricity to scale AI. But that misses the point entirely. The true innovation lies in rethinking the very architecture itself, making it inherently more intelligent, not just more brute force powerful. This fundamental rethinking is precisely what led to the quiet revolution of sparse attention. It's an often unseen architectural innovation working silently behind the scenes, yet its impact is profound. Sparse attention is, in essence, a clever trick to bypass the quadratic trap without sacrificing the LLM's ability to understand context. Instead of every word paying attention to every other word, sparse attention models learn to be selective, strategically focusing their computational resources only on the most relevant pieces of information. It's about efficiency not through brute force, but through intelligent design. It allows LLMs to stretch their context windows dramatically, processing far more text, without the exponential explosion in cost and memory. So, how does this selective focus actually work? Think back to our orchestra. With sparse attention, not every musician is trying to listen to every other. Instead, specific sections might listen primarily to their section leader, and only occasionally to the conductor or certain key instruments. The LLM still processes information, but instead of forming a dense web of connections where every single word talks to every single other word, it creates a sparse, targeted web. Some connections might be fixed, following a predefined pattern, perhaps only paying attention to immediate neighbors or to a few key words throughout the entire text. Others might be learned, where the model itself determines which connections are most important during training. It's like shining a focused spotlight on the critical elements of a sentence, rather than flooding the entire stage with light. This drastically reduces the number of calculations needed, transforming that quadratic growth into something much more manageable, closer to linear growth. Now, sparse attention isn't a magic bullet. The core challenge lies in deciding which connections to keep and which to ignore. Make the wrong choices, and the model might miss critical context, leading to errors or a loss of coherence. This is where the unseen work of researchers truly shines. They explore diverse strategies. Some models use fixed, predefined patterns of attention, like focusing only on words within a certain window or at specific distances. Others employ more sophisticated learned patterns, allowing the model to adapt and determine the most relevant connections on its own. Each approach comes with its own set of trade-offs, balancing computational savings with the risk of reduced accuracy or increased complexity in design. This ongoing innovation, this constant refinement of how an AI pays attention, is a critical, yet largely invisible, frontier in making LLMs smarter and more practical. The implications of sparse attention extend far beyond mere technical elegance. By dramatically reducing the computational and memory requirements, this unseen architecture is quietly democratizing access to powerful AI. It means LLMs can run faster, on less expensive hardware, with a significantly smaller carbon footprint. This isn't just about saving money for tech giants. It's about making advanced AI accessible to smaller businesses, researchers in developing nations, and even individual creators. It transforms LLMs from prohibitively expensive supercomputers into practical, sustainable tools for a much broader audience. Sparse attention is the invisible force pushing AI beyond the realm of giant data centers, into a future where powerful intelligence is not just bigger, but smarter, leaner, and truly available to everyone. It's making the revolution silent, but its impact will be heard around the world.